Hello everyone, and welcome to the Week 13 Math 2419 review. This is going to be the final weekly review of the semester. And this weekly review will be covering the alternating series test, the ratio test, the root test, and what a power series is. All right, so let's go ahead and get started. And that does say ratio test. So perfect. First off, we'll start with the alternating series test. This is a bit of a review. I covered it last week, but we'll go over it again because it is important, especially when you get down to absolute versus conditional convergence. So with an alternating series test, as the name implies, you need to use it on an alternating series. So let's say we have some kind of series, and it has the form some part that makes it alternating, in this case -1 to the n, times some sequence a sub n. And importantly, this a sub n sequence is always positive, or non-negative. It could technically be 0, but then that doesn't really make much of a difference. Well, then we can say that this power series converges if two conditions are met. And that first condition is the limit as n approaches infinity, a sub n is equal to 0, so it passes the nth term test. And our second condition is that every term is smaller than the term that came before. It could be equal to, but it cannot be greater than. So we'll do a quick example. And if both of these conditions are met, your power series converges. If they are not met, then your series will diverge. So let's take an example. Let's say we have the sum from n equals 1 to infinity of -1 to the nth times n factorial over n to the nth. Well, what we need to do is we need to show, first off, we can clearly see that it's alternating because of this -1 to the nth. So we need to show two things. First, that the limit as n approaches infinity of n factorial over n to the nth is equal to 0. And what we can do is we can actually use a comparison and say, well, n factorial over n to the nth is always going to be less than or equal to n to the n minus 1 times 1 over n to the n. And what we're doing here is we're essentially writing out all the terms. So if we wrote out n factorial on the top, we would have n times n minus 1 times n minus 2, and so on, all the way down until we get down to 1. And on the bottom, we would basically have an n for every single one of these. So what I'm doing in this comparison right here is I'm taking these smaller terms, these n minus 1, n minus 2s, and replacing all but this last one with n's. And what that does is it gives me an n to the power of n minus 1 over n to the nth. And simplifying this, I would get that this is simply equal to 1 over n. And of course, we know that this is larger than 0, or n is positive. Well, then I can take the limit and say that my limit as n approaches infinity of n factorial over n to the nth has to be smaller than my limit as n approaches infinity of 1 over n, because n factorial over n to the nth is smaller than 1 over n. And this limit is, of course, 0, and because n factorial over n to the nth is always positive, well, this limit would also have to go to 0. So the first condition for our alternating series test is satisfied. The second condition is we need to show that each term is bigger than the last one, or smaller, sorry. Each term is smaller than the one that came before it. So we would simply plug in an n plus 1 wherever we see n, and say that has to be smaller than n factorial over n to the nth. Well, if I cross multiplied, then I would get n to the nth times n plus 1 factorial is smaller than n factorial times n plus 1 to the n plus 1. Now I can cancel out, or I guess I can simplify like so. I can rewrite my left-hand side as n to the nth times n plus 1 times n factorial. And my right-hand side is n factorial times n plus 1 times n plus 1 to the nth by reducing this exponent by 1. And now I can cancel an n factorial from each side as well as an n plus 1. And that leaves me with the statement that n to the nth should be less than n plus 1 to the nth, which is clearly true for all n that are positive. So our second condition is also satisfied. Then we can say, because both conditions are satisfied, our power series, or our series, will converge. Now, we want to know, would this series converge if it wasn't alternating? So does this series, the sum from 1 to infinity of n factorial over n to the nth, converge? And if it does converge, then we say that it converges absolutely. But of course, if it does not converge, then we say that our original sum, n equals 1 to infinity of minus 1 to the nth, n factorial over n to the n, we say it converges conditionally. And what this condition is it has to be alternating in order to converge. All right. Now, we'll go ahead and do a couple of practice problems. State whether the series converges conditionally, absolutely, or does it diverges? Just one, I think. Two. That'll be negative 1 to the nth divided by the natural log of n. I'll give you a minute or so to work on that. All right, time to go over this problem. Remember, for it to pass the alternating series test, these two conditions need to be satisfied. First, the limit as n approaches infinity of 1 over the natural log of n should be 0, and it is because the natural log of n approaches infinity, so 1 over infinity gives us 0. Second, we need to see that 1 over the natural log of n plus 1 should be smaller than 1 over the natural log of n. By cross multiplying, this gets that the natural log of n is less than the natural log of n plus 1. If we raise both sides to the e, we use exponentials to cancel that, we get that n is smaller than n plus 1, which is, of course, true. So it passes the alternating series test, so we know that it converges. Now we just need to see whether it converges conditionally or absolutely. And to do that, we would need to look at it when it was not alternating. So the series 1 over the natural log of n, simply by itself. And in this case, I'm going to use a direct comparison test. I know that n is larger than the natural log of n, so then 1 over n should be smaller than 1 over the natural log of n. But then I know that the sum from 2 to infinity of 1 over n diverges, and because it's smaller, that tells us that the sum from 2 to infinity of 1 over the natural log of n should also diverge. So because the alternating series converges, but the non-alternating series does not, we say that our series converges conditionally. All right. That's probably enough of the alternating series test. So let's move on to the ratio test, which is one of my favorite of the series tests. And the ratio test tends to be good for things like factorials and exponentials. Good for factorials and exponentials. Okay, so what is the ratio test? Answer first. So let's say we have a series, and it's the sum of all terms in some sequence a sub n. Well then, if the limit as n approaches infinity of this fraction, which we're going to call a sub n plus 1 over a sub n, is smaller than 1, we say that our series converges. If it's larger than 1, it diverges. And if it's equal to 1, our test is inconclusive. And you would need to apply a different test. So this might look a bit confusing, so let's try an example to help clear it up. In fact, we're actually going to use the exact same series from part 1, but not alternating. Sum from 1 to infinity of n factorial over n to the nth. And if you'll recall, previously we solved this by looking at simply using the alternating series test. But if we wanted to make sure that it was convergent conditionally or absolutely, then we would need to find the convergence of this series here. And this is actually a perfect instance to use the ratio test because we have a factorial and an exponential. Well, we need to take the limit as n approaches infinity of a sub n plus 1, so that would be n plus 1 factorial over n plus 1 to the n plus 1th power, divided by a sub n, so n factorial over n to the nth. Now, fractions and fractions are a bit irritating, so it's usually helpful to just write it as multiplying by the reciprocal, and this gives us n plus 1 factorial over n plus 1 to the n plus 1 multiplied by n to the nth over n factorial. All right. Now, of course, we want to simplify this as much as we can. And to do that, we could take out an n plus 1 multiplied by n factorial. Then we have n plus 1 times n plus 1 to the nth multiplied by n to the nth over n factorial. What can we cancel? Well, we can cancel an n plus 1 from top and bottom as well as an n factorial. Cool. Now what are we left with? Well, this is actually a bit tricky because it requires a bit of careful observation. I'm going to drop the absolute value bars and just use parentheses. And from here, I'm going to do a bit of tricky rewriting. First, I'm going to take out the exponent of n, so that's around everything. And then I'm actually going to, that should be an n plus 1. And what I'm going to do now is I'm actually going to flip my fraction by making it a negative exponent. And that would give me n plus 1 over n to the minus n. Then I'm going to break apart my fraction, so that would give me n over n, which is just 1, plus 1 over n, still to the minus n. Now, if you recall, this is actually the definition of e to the power of minus 1. Because the number e is actually defined as the limit as n approaches infinity of 1 plus 1 over n to the power of n. Because I have this negative, that would make it an e to the negative first. And 1 divided by e is a little below 3, so it's between 2 and 3. So 1 over, let's say, 2.5 is, of course, smaller than 1. Because this ratio is smaller than 1, we say that our series converges. Cool. All right. Time for, I think, a couple of practice problems. I'll give you 2 this time. Start at 0. That'll be the first one. The second one, say the sum from 1 to infinity of some number k, where k is a constant. And that means your answer will be based off of k in the end. I'll give you a couple of minutes to work on that. All right, let's go over these problems. This first one, fairly straightforward, has an exponent and a factorial, which means it's a great time to use the ratio test. We want to do a sub n plus 1, which would be 2 to the n plus 1, over n plus 1 factorial, divided by a sub n, so I'm just going to multiply by the reciprocal, which would be n factorial over 2 to the n. Now to simplify this a bit, I can, of course, take off one of the 2's, make that 2 times 2 to the n over n plus 1 times n factorial, multiply by n factorial over 2 to the n, simplify wherever I can, and that leaves me with the limit as n approaches infinity of 2 over n plus 1, which is, of course, 0. So this tells us that the series converges because 0 is less than 1. All right. For the second one, here we go. For the second one, we want to, of course, take the limit as n approaches infinity of k to the n plus 1 over k to the n, which would be a sub n plus 1 over a sub n, which is, of course, the limit as n approaches infinity of k times k to the n over k to the n, which gives us just k, where k is a constant. Now, if you'll recall, technically this would be the absolute value of k. Now, if you'll recall, our series will converge if and only if this value of k is smaller than 1. So we can say that our series converges for values of k that are between -1 and 1. If k is equal to 1, well then our ratio test is inconclusive. And if k is greater than 1, well then, of course, it diverges. But we can also say that if k is equal to 1, then the limit as n approaches infinity of 1 to the nth is, of course, just 1, so it fails the nth term test, so then it would diverge then. And you'll notice this is actually like the geometric series test. It tells us that our series will converge only if this value k is between -1 and 1. So that's one way you can actually get the geometric series test. You can get it from other tests as well, but I just like to use that as an example because I think it's neat. All right, that's probably enough of the ratio test. Let's move on to the root test. And the root test is actually really similar to the ratio test. Again, it's really good for exponentials. In fact, in most cases you can use the root test. You can also use the ratio test. Not necessarily vice versa. The root test isn't great with factorials, but it's good for exponentials. Let's start with the definition. Let's say, once again, you have the sum of some series, or some sequence a sub n, and we can say if the limit as n approaches infinity of the nth root of a sub n, the absolute value of a sub n, I should say, is smaller than 1, your series will converge. If it's larger than 1, your series will diverge. And if it's equal to 1, then the test is once again inconclusive. So pretty similar to the ratio test in that regard. Now, as a quick example, let's say we had the sum from 1 to infinity uh, 4 to the 2n, 4 to the 2n divided by n to the n. Well, I'm going to write this 4 to the 2n over n to the nth like so. 4 squared the nth over n to the nth, which is 16 to the nth over n to the nth, which is 16 over n to the nth power. Now I'm going to apply the root test. Well, because I did this work to rewrite my sequence, I can see clearly that my nth power on the inside and my nth root will just cancel. And I'm left with simply this statement, which is, of course, 0. So my series would then converge. All right. And if you wanted to, you could apply the ratio test here as well. I tend to prefer using the ratio test just because I find it easier and more applicable in more situations. But the root test is also a good option. Now let's go ahead and do a practice problem. Go ahead and apply the root test to see if that converges, and I'll give you a couple minutes to do so. All right, this problem is once again fairly straightforward. It's already in a good form for us to just apply the root test immediately. And with this limit, it's of course a balanced rational function, so we can just use the coefficients of the largest term. In this case, n over 2n gives us 1/2 And because that is less than 1, we can say that our series will converge. Easy enough. All right, that's probably enough of the root test. Because, like I said, fairly straightforward. And that will bring us to the last major topic. That is power series. All right, a power series is, in short, a function represented by an infinite sum. So it is a bit more complicated than that, but it would look something like this. Some sequence multiplied by some little function of x. And usually that will look like x minus c to the power of n. Occasionally you'll see it as just x to the n, so basically where c is equal to 0. And if we wrote out terms for this, it would look like this. Minus c's. And this is basically an infinite polynomial. Now, the really useful thing about this power series is it can actually be used to represent any non-polynomial function, or at least a lot of non-polynomial functions. For example, you can actually write cosine and sine as infinite polynomials using a power series. And that actually gives us a lot of flexibility, and that's why it can be really useful. Some terminology. We say that c, this minus c bit right here, that's where we get our c value, is called the center of our power series. Or we could say that it's centered at c. Now then, the interval of convergence would be all the x values such that the series converges. And the radius of convergence is how far x can be from the center and still converge. So if we wanted to draw it out on a little number line, we would have all real numbers. Our power series would be centered at one value. It would converge on any x value within the interval, and the radius would be this distance from one edge to the center. This whole thing would be the interval. All right, let's take a look at an example. Let's say we have a sum from n equals 0 to infinity of x plus 2 over 4 to the nth. Now, if I wanted to write this in a bit more of a formal way, I could write it as x divided by 4, sorry, not x divided by 4, 1 divided by 4 to the nth power times x plus 2 to the nth. And in this case, this little 1 over 4 to the n would be my a sub n. Well, then I could write out, clearly I can see that my center's at -2. One easy way to find the center as well is the value of x that will make your sum equal to 0. So if I plugged in x is equal to -2, then I would have -2 to the nth for all powers of n, or sorry, 0 to the nth, which is 0 for all powers of n, which would mean that every term in my sum is 0, and I just have 0 plus 0 plus 0. My sum would be 0. So that's another way you can look out for the center, what values would make your whole sum 0. Well, I can actually, and on a different note, if I say that this is some function of x, because it is, I can evaluate it just like a normal function. If I plug in x is -2, well then I get the sum from 0 to infinity of 1/4 to the n times just 0, which is 0. If I plug in 0 for x, well then I get 1/4 to the n times 2 to the n, which is 1/2 to the nth. And I can evaluate that using my geometric series rule. I would get 1 over 1 minus 1/2, which gives me 2 as a sum. And that would be my function value at 0. Now, if I wanted to find the radius and interval of convergence, I would use the ratio test. If I apply the ratio test, I get that should be an over 4 right there, not over n. Well, then I would get x plus 2 over 4 times x plus 2 over 4 to the nth, and combined, this part here would be my x plus 2 over 4 to the n plus 1, which would be a sub n plus 1. Then I would be dividing by x plus 2 over 4 to the nth. I'm going to write that as the reciprocal because that's how I prefer to do it. And from here, I can clearly see that these things are going to cancel. And that gives me the limit as n approaches infinity of the absolute value of x plus 2 over 4. Because there aren't any n's in this, this actually just gives me the absolute value of x plus 2 over 4. Well, I know that my series will converge as long as this x plus 2 over 4 is smaller than 1. If I multiply both sides by 4, that tells me that x plus 2 has to be smaller than 4. And what this 4 value right here is this 4 is actually my radius of convergence. To find the interval, I would have to actually solve this equation, absolute value of x plus 2 is smaller than 4. So I'd say that x plus 2 is, of course, larger than -4, and x plus 2 is smaller than 4. So that gives me x is larger than -6, and x is smaller than 2. So my interval would be all the x values between -6 and +2. And because my center is at -2, you can clearly see that there's a distance of 4 up to +2, and 4 up to 4 down to -6. So just to conclude, my center is at x equals to -2. My radius is 4. And my interval, well, there is one last thing we should do before stating our interval, and that is check the endpoints. Because remember, if the magnitude of x plus 2 over 4 is equal to 1, then our test is inconclusive. So you should always check your endpoints when finding your interval of convergence. In this case, our endpoints give us a sum from 0 to infinity of first -4 over 4 to the nth, which is -1 to the nth, and this fails the nth term test. So we can see that x equals -6 is not in the interval. And likewise for the other endpoint at +2, we would get 2 plus 2 is 4 over 4 to the nth, and that also fails the nth term test. It is not an interval. So neither of our endpoints were in our interval, which means that our interval is from -6 up to +2, not including the endpoints. All right. Now, time for some practice problems. Find the center, the radius, and interval of convergence. And I'll give you a couple of minutes to work through those. All right, let's go over these problems. So to find the center and the radius and the interval, we'll start with the first one. I'm just going to do it right over here on the right-hand side. So if you wanted to find the center, well, that's fairly easy. It's already in a nice form for it. You can see that our center is at x equals to 1. Now, if we wanted to consider the radius, we would apply the ratio test. And that would give us 1/2 times 1/2 to the nth. I'm doing some simplification as I go, times x minus 1 times x minus 1 to the nth, divided by 1/2 to the nth times x minus 1 to the nth. And this is a sub n plus 1 over a sub n. Cancel whatever we can. And that gives us a limit of x minus 1 over 2, which should, of course, be smaller than 1. Now, if we continue to solve this, we get that the absolute value of x minus 1 is smaller than 2. So x minus 1 is larger than negative 2, and x minus 1 is smaller than 2. That tells us that x should be larger than negative 1, and also x should be smaller than 3. So our radius would be this number here. And for our interval, we would have to plug in our endpoints. When x is negative 1, we would have negative 2 to the n times 1/2 to the n, which gives us negative 1 to the nth. Because that fails the nth term test, it diverges. Same thing when x is equal to 3. We would get 2 over 2, which is 1 to the nth. So our interval would just be negative 1. Oops, not inclusive. Negative 1 should be smaller than x, which should in turn be smaller than 3. That would be our answer for number 1. For number 2, here we have clearly, once again, our center should be at 7. Sorry, negative 7, because that would make all our terms 0. To find our radius, we need to apply the ratio test, and that would give us x plus 7 times x plus 7 to the nth over n plus 1 times n factorial all over x plus 7 to the nth over n factorial. Simplify what we can. That leaves us with the limit as n approaches infinity of the absolute value of x plus 7 over n plus 1. And in this case, since we're using the limit as of just n, this would actually be 0 exactly, because we treat x like a constant, so this would make it bottom heavy. And 0 is always less than 1, regardless of the value of x. So this tells us actually that our radius is infinite, because we can have any x value. And that also tells us that our interval of convergence would be all real numbers of x. Because no matter what x value you plug in, this limit's always going to go to 0, which means it'll always converge by the ratio test. So for number 2, we've got a center at negative 7, but an infinite radius and all real numbers as our interval of convergence. Now finally, for our last one, we have from 1 to infinity of x plus 2 to the nth over n squared. Again, our center is fairly easy to find. It's at negative 2. If we apply the ratio test, we would get the absolute value of x plus 2 times x plus 2 to the nth over n plus 1 squared, and then we would divide by x plus 2 to the nth over n squared, so I'm just going to multiply by the reciprocal n squared over x plus 2 to the nth. Again, cancel what you can, and this gives us the limit as n approaches infinity of the absolute value of n squared times x plus 2 over n squared plus 2n plus 1. Now, in this case, you would take the coefficients of the largest terms because this is balanced, and on top your coefficient is x plus 2. On bottom your coefficient is 1, and that needs to be smaller than 1. Now, this 1 here would be our radius, which means our interval would be our center plus or minus our radius. We could also see that by solving this equation. X plus 2 should be larger than negative 1. Also, x plus 2 should be smaller than 1. So x should be larger than negative 3 and also smaller than negative 1. Now we also need to check our endpoints. In the last one, because our radius was infinite, we didn't have any endpoints, but in this case, we do. So let's plug in negative 3 for x. And in this case, we would get negative 3 plus 2 is negative 1. So negative 1 to the nth over n squared. Well, we know that 1 over n squared converges by the p-series test, so the alternating form should also converge. So this converges, which means that x equals to negative 3 works. Similarly, if we plug in x is equal to negative 1, that would give us negative 1 plus 2 is 1 to the nth, which is 1 over n squared, which also converges. So x is equal to negative 1 also works. So this tells us that our interval, in this case, includes endpoints. And it would be the interval from negative 3 to negative 1 inclusive. And that is how you find the radius and interval of convergence of some power series. The ratio test is very helpful in these cases. Well, that's all for today. So thank you for watching and have a nice day.